Are there questions? Yes. Any? Term paper topic. So I was thinking of doing it at the end of this month. Some topics I can already say, for example, the Hubble tension, right? I mean, Hubble tension basically is the observation that there seems to be discrepancy in the measurement of the Hubble parameter today between early universe measurement and late universe measurement, right? So late universe is basically by looking at the stars and galaxies, well, nearby in the sense that not very nearby, right? But say Z, which is not too large, right? That's one measurement. The other measurement is that you basically look at the cosmic microwave background radiation and then adjust the Hubble parameter to fit what you observe, right? And there seems to be a discrepancy between these two. Right? So that's one topic which in fact has a both theoretical part and experimental part. So the experimental part is just an observation, right? What observation do you make and to see this discrepancy, right? The near the small low Z and high Z measurement. The other one is the theoretical part, which is that assuming that this discrepancy is there, what can we do to, can we modify cosmology to account for this discrepancy, right? So those are two possible topics, right? Then the one is axionic dark matter, for example, which we haven't introduced so far, right? So maybe I'll not say very much more about this, but you will see later the various dark matter candidates. So axionic dark matter is one possible dark matter candidate, which I'm not going to discuss in detail in this class. So that's one topic. Right? Then the distance measurement, right? That's one. How do you actually measure? We have been talking about measuring distances, right? Because otherwise you cannot do any cosmology. You cannot get any data on cosmology unless you know the distance to objects, right? And how exactly it is measured, right? So that's one possible topic. And okay, I'll try to find out other topics later, but you can also choose your own topic. It doesn't have to be chosen from any of these. Right? There are more advanced topics in inflation, but those require more, a deeper understanding of quantum field theory and so on. Right? Like for example, non-Gaussian fluctuations in the early universe. Right? So those will leave out, but in case you want to do this, you are welcome to do it. Right? So you also try to think of the topics you might want to choose. Right? And at the end of this month, I'll try to make a list of topics and I'll distribute them, and then we can also discuss them in the class.
So we have to do some.
That's right, yeah. So survey some calculations, or even just, as I said, just observations, right? How you measure distances, for example, right? And then just present it. Is that okay? Well, there's nothing to explain in the sense that there is no observation so far, right? But yeah, so that's certainly one topic, right? That what kind of processes could possibly produce primordial gravitational waves, and what will be their consequences, right? That how can you test such? Yeah, that's certainly one topic you can choose if you want. Yeah, so it doesn't have to be standard cosmology, right? There are various proposals for non-standard cosmology, right? You can also choose any of them. Any other question? Or anything else? No?
Yeah, I just wanted to make a comment that the visa that is coming, that next generation gravitational wave, they expect that we may actually detect primordial gravitational waves.
Okay, yeah.
Yeah, it is an expectation.
Okay, yeah. So, but that of course requires models of what process could produce primordial gravitational waves, right? So that, yeah, so that kind of study you can certainly do. Yeah. Yes.
As a condition for equilibrium, that we are saying that at least more than one collision should be there within the Hubble time.
Yes.
In the reactions. Why we choose that sort of a criteria? Because in a sense, this one collision seems very less for equilibrium.
Okay, one collision, you should remember how you define the cross section, right? It's not just one collision that changes, that does what you want, right? So most collisions will not do what you want, right? For example, if you want to change P to N, right? We are not calculating the total. So when you talk about sigma, it's for the total probability of P colliding with something, right? We are counting only those which convert P to N, right? So then one collision means the probability of this happening in one Hubble time is of order 1, right? So that's a good guideline, right? Because that means it's most likely going to change to N, right? And if it's 10, for example, then it's very, very likely that P will get changed to N several times.
We are comparing this with the Hubble time scale because as the various processes start happening, there can be many time scales involved.
Yeah, you're comparing with the Hubble time scale because Hubble time scale is the time scale in which the densities fall off, right? Universe doubles in size, right? So if the process is lower than Hubble time scale, right, then there is no hope of getting to equilibrium because by the time that process happens, the universe has changed its state, right? All the densities, etc., that you use in your calculation are not correct anymore, right? So that's why Hubble time is a good reference point. But this 1, of course, is an arbitrary choice, right? That you can, instead of 1, you could choose 5 or 5, 10, whatever you want, right? But it's order 1, so that's the guideline which tells us when this decoupling happened. Any other question? Okay, so let me remind you what we had obtained so far. So what we saw is that the nucleosynthesis begins and ends at T of order 10 to the 9k up to 10% margin. Okay. And the end of nucleosynthesis, end basically is the point where happens when free neutrons are exhausted. Okay. And during the process in which it's happening, right, let me emphasize this again. During the process when this nucleosynthesis is happening, right, the picture is that all the other species like D, Ag3 and H3, right, they are kept at their critical density that is needed for the equilibrium to establish. Okay. But they never exceed their critical density because as soon as they reach the critical density, they started getting converted to helium, right? Ultimate destination is helium-4, right? As you saw, that has a much larger fraction in the equilibrium situation, right? So as soon as the density of anything exceeds the critical density, right, it starts getting converted. Eventually, it forms part of the chain and gets converted to helium. So this marks the beginning, right? During the process, these densities remain more or less fixed at those critical densities. And then when it ends, the densities get frozen to the critical densities, right? Because the nucleosynthesis has stopped. For example, the D, let me write down those processes, D plus D going to H3 plus P and D plus D. And then the other processes also decomp plus 83, etc. Okay, the various processes that we saw. So once the neutrons get exhausted, okay, no further D is being produced, okay, As a result, the density of D falls below its critical value, and these processes stop. Right? Because now you can't, the universe expands at a faster rate than these. Right? So these processes stop. And so the D, as well as the other objects, He3 and H3, basically gets frozen to whatever those critical densities were. Right? This is the rough picture. So the density of D as well as H, all the intermediaries, right, the hydrogen 3 and helium 3, will get frozen to those critical densities. Is this picture clear?
So similarly for neutrons, the initial reaction of proton plus neutron will give neutrons.
Yes.
So in that reaction also there should be some critical density for the neutrons required, right?
Well, the point is that when you're talking about neutron converting to something else, the critical density is that of what it's colliding with, right? So as long as there are enough protons, each neutron has a probability of making that transition, right? And proton is not depleted. Proton is depleted, but it always remains of order 1, right? The proton density. So neutron conversion happens fully, right?
More or less all the neutrons will be
More or less all the neutrons will be gone, exactly. Right? All the free neutrons will be gone. Right? But D requires another D to collide and form heavier elements. Right? That's why once the neutron stops, right, the D cannot grow anymore. Right? Or it cannot collide anymore. So whatever D, so D cannot grow anymore. So D gets frozen to whatever it was, right? Critical density. Because once the density falls below that, then these processes become inefficient. Right? These processes cannot remove D anymore from this. So at when nucleosynthesis ends, ND is determined from sigma total. Let me write this explicitly. Sigma D goes to something. So the sigma basically is the sum of these two. Okay, let me just call it sigma D. Right? That's the definition of sigma D. It's total cross section. Maybe yesterday I called this something else. This total cross section of D plus D going to H3 plus P, or D plus D going to H3 plus N. So this is telling us the probability that so this quantity is telling us the rate at which D is getting depleted, right? Because rate at which D collides with something else, and that has to be of order h, right? If it's less than h, then this process will stop. So this you can then use to estimate what ND should be, right? Because everything else is known. So sigma D times V, this we wrote down 3.4 times 10 to the minus 17 centimeter cube per second. H, let's write it down, this 8 pi g over 3 AB over 2 t to the 4 times 2 plus 6 times 7 over 8 t nu over t to the 4. and that's it, right? So this determines ND. So let me write down the expression for ND. So this is okay, H over sigma total V. Okay, so H we know, H is given here, sigma, this is I'm calling sigma dV. Sigma dV is given here. Okay, so you can find what ND is from this calculation, from this ratio. First two reactions, yes.
D plus H3 and D plus H3.
Yeah, the point is these are all of the same order, right? D plus H3 is not relevant for deuteron depletion, okay, because we are trying to calculate the number density of deuterons, right? So this reaction doesn't depend on ND. The rate at which deuteron is going away, right? This depends on NHE3. So this will determine NHE3, right, and NH3. That once those densities fall, right, then that means that He3 and H3 are no longer being converted to He4, right? So those densities get frozen there. Right? And the point is, because these are, in fact, we'll discuss this, these will be of the same order as this, okay, because all of them are strong interaction, right? So that already suggests that the final density of He3 and H3 will be of the same order as that of D, right? Because you see the same formula will work there, right? Except that you will replace sigma D by that corresponding cross section, and instead of ND you will have the N of He3 or H3, right? Because the number of collisions of deuteron will depend on the densities of these, right? So the same formula determine the densities of He3 and H3, and it will be of the same order because the cross sections are of the same order. All are strong interaction cross section, right? This 10 to the minus 17 will be there even for these other two reactions. Is this point clear? Right. So this we will discuss later. Right. Right now, let's just do this to fix ND.
But when will that reaction stop? Like B plus D going to other products?
Yes.
That will stop when the neutrons will stop.
Exactly.
Exhausted.
Yeah.
This process will stop later, right?
Yeah. So well, later means it happens or more or less at the same time, right? Maybe a little later. Okay. The point is that so once these go out of equilibrium, no more He3 is being produced. He3 and H3, right? So their density will now start fall below the critical density. See, they are frozen at the critical density during this process, right? Because as you said, once you get to the critical density, you immediately get converted to the helium-4 at the end, right? So these are all kept at the critical density during this process, right? And once the neutron production stops, then the D gets frozen, right? Then this process goes out of equilibrium. These also get frozen, and well, not these processes, right, will also go out of equilibrium, because as soon as the production stops, the densities start falling, right? But they cannot fall below the critical density. So they basically get frozen to the critical densities. Right? That's the picture. And the critical densities of D, He3, H3 are all the same or approximately the same, because the cross sections are of the same order.
Sigma D is the same.
Exactly. The sigma times V is the same. Same meaning of the same order. Right? That's the reason that this kind of argument you can use to figure out the order of magnitude of the critical of the relic densities. Okay? The actual calculation, I mean, if you want the this time, right, you cannot get up to 10%. You can get only up to order 1. Right? Because when you say this is of order 1, this could be 2 or half, right? That as we discussed. And that will have an effect on ND. Right? And ND could be twice what you calculate from this formula or half of what you calculate from this formula. Right? So to actually calculate ND, right, not just the order of magnitude estimate, you have to run the differential equation. The differential equation knows everything, right? Because you are trying to calculate how ND, NHE, NH3 and N helium-4 all grow, right? And so that will give you the accurate result for what the relic densities will be. Is that point clear? Okay. Nevertheless, I'm going through this because I want to see the dependence on the omega b. So let's go through this anyway. So we are going to compare this with the total number of nucleons, which is the number of neutrons plus protons, and this we have derived the formula. Let me write this: T over T naught cube times omega b rho c over mp, which I can write as T over T naught cube times omega b 3h naught square over 8 pi g mp, right? Because rho c is 380 square over 8 pi g. So Nd over Nn, right? This you can relate to direct observation. Nd over Nn will be given by 1 over sigma total V times this object H square root 8 pi g over 3 AB by times okay, I just divided by Nn. And if you want to calculate Nd over Nh, right, that's Nd hydrogen density, right? We saw that it's by mass it's 73%, right? So you can calculate 0.73 times Nn. Okay, the hydrogen density today, and so you can, so it's roughly the same order as this. The point that is we want to extract from here is that you see the Nd over Nn is proportional to 1 over omega b h square. Right? Let me remind you, h is given by h0 divided by 100 kilometer per second per megaparsec. Okay, but Nd over Nn is given by 1 over omega b h square, right? Because all the rest are independent of what omega b and current h are, right? These are all T we have already determined, right, which is 10 to the 9 Kelvin. T naught we know, right, 2.73 Kelvin. And then these are of course microscopic results. Yeah, and everything else is known here, right? So it depends on this ratio 1 over omega b h square. And so then this gives a way to restrict omega b h square from observed data. If you know observationally what Nd over Nh is, then that can be used to restrict omega b h square. So let me write down the result, so numerical result. And this dependence will be there also in the numerical result, right? The numerical result will, you just evolve the number densities and you get the final Nd, and but when you have divide by Nn, right? See, this omega b h square is coming basically from Nn. Right? This you cannot do anything about. This you don't need numerical data. Right? It is just based on current observation. So numerical result for Nd over Nh is about 2.07, sorry, 2.57 times this is for this is roughly what we believe it to be today, right? Omega b is 0.04 and h is 0.7, so h square is 0.7 square.
This NDO and NH is observed today.
It is supposed to be observed today, but this is the result that I am quoting that you get by numerically evolving this.
Numerically evolving.
Yeah, those. So as I said, that this equation, that this kind of argument can only determine ND to up to order 1 corrections, right? Order of magnitude it can give, but it could be twice this or half this, right? But accurate results you can get by numerically evolving those equations, right? So this that I am quoting here is a result that you get by numerically integrating those equations, right? The equation for the various number densities. Right? Otherwise, I couldn't have written this 2.57, right? I would have said that this is of order 10 to the minus 5. Right? So, get this 2.57, you really need the numerical data. So, now by comparing this with observation, right, and the point is indeed we find that this result agrees with observation. The way this ND over NH is observed, right, and the same thing is true for the hydrogen to helium ratio, is that you look at parts of the universe which have no heavy elements, right? Because heavy elements we know are produced in stars, right? And if some part of the universe contains heavy elements, right, that means that has gotten polluted by some dust from the star, right? Maybe one star exploded in supernova and that dust spread over to populate these heavy elements. Okay. So absence of heavy elements suggests that that part has not been polluted by later production in stars. Right? So whatever ratio you see, right, hydrogen to helium or hydrogen to deuteron, that is what is the primordial ratio, right? Whatever it was at the time of nucleosynthesis, that has survived, right? Because later production in stars are not relevant. Right? As we'll discuss later, that all the heavy elements are basically produced in stars. You cannot produce in the primordial nucleosynthesis. So that's the way you observe this, and it agrees with this number, right, up to experimental errors. And that tells us that this omega b h square cannot be very different from 0.02. Yes. Temperature? Temperature here in this calculation, yes, temperature is 10 to the 9. Right? But in numerical analysis, you don't have to put that in, right? That will automatically tell us where the thing gets frozen, right? Because there you are simply evolving the d and dt and as a function of time. Right? And at some point you will find that they are getting frozen, right? In the sense they now go as 1 over lambda cube, right? That's the way. So the ratios get frozen, right? And that's the data you use, right?
Because we have to put some cutoff, like after this point, these reactions will not.
You know, numerical results, you know it, right? See, if you numerically, what are you doing? You are writing d and dt equal to the rate of production and rate of annihilation, right? So there you don't have to do anything, right? Nothing switches off. Everything is there all the time, right? The switching off happens because the Ni has fallen, right? Ni is on the right hand side. So if you use this numerical analysis, right, you don't have to assume anything, right? You just put in the reaction rates from microscopic result and then just evolve this as a function of time, right? So this idea of figuring out when it begins, when it ends, right? All those are because if you want to be lazy and don't want to do numerical analysis, right, you can still get a reasonably good answer just by doing that kind of argument, right? And as you saw for hydrogen to helium, you can actually get the answer quite accurately, right? Up to 4% accuracy, we can get the result, and that's because it's a very highly sensitive function of temperature, right? So we have a very good idea of when it begins and when it ends within 10% error in the temperature. But that is not the case for the others, right? For the others, this argument says that you are using this order 1, and this order 1, if you change it to order 2 or order half, the result will change. Right? So for this analysis, you can only get an order of magnitude estimate for the relic densities by doing this kind of analysis. But once you put it on a computer and follow it as a function of time, you will find that at large time the ratios get frozen. Right? And that will tell you that nucleosynthesis has stopped.
You said this ratio you determine numerically, right? Numerical integration.
Yes, basically ND you determine numerically. NN you determine from extrapolating back, okay? Because you already know the number of nucleons. See, that is an input that you have to give, right? The baryon asymmetry is not generated by this process, right? So how many protons and neutrons are there total? That is something that is based on present observation, omega b. That is an input to this system of equations.
I'm asking, you did numerical integration, so why there is plus minus 0.08?
Oh, because numerical integration also has errors, right? The various measurement errors in sigma and so on.
Sigma was determined analytically, right?
No, these cross sections. These cross sections, see, everything has error, right? So all these cross sections are input in the numerical result. See, on the right hand side, when you want to calculate the right hand side, right here, in the right hand side, the cross sections are going in, because you have to calculate the rate of depletion minus rate of production. Right? Those all depend on the cross sections, right? And all those have errors.
Cross section you determine experimentally.
Experimentally, yeah. Right? Because nuclear cross sections are hard to determine theoretically. Right? You can, of course, you can do it, right? But again, those will have their own theoretical errors.
Theoretical errors due to?
Because you can't solve things exactly, right? You always have to make approximations. See, except for hydrogen atom, there are very few things you can actually solve exactly, right? And even hydrogen atom, right? You cannot really solve exactly, in the sense that we know that the higher levels are unstable. Right? If you put a hydrogen atom at a higher level, it will eventually decay down to lower level. Quantum mechanics is not saying this, right? So yes, the reason that it's unstable is because you haven't made an approximation in getting those energy levels of the hydrogen atom. The quantum electrodynamics will tell you that these decays take place. Right? So anything that you do, right, you always make approximation, right? Even if you do it theoretically. Yes. Coupling, okay. QCD coupling constant you determine experimentally. That's one data, right? But these are not more data than. So it's not that everything. Yeah. So in principle, everything is determined in terms of that, right? Or what we call QCD lambda, the one energy scale. But you certainly need more than this in doing these calculations, because you will do the calculation approximately. Yeah. So cross section. So what I'm saying is that. So what you are saying is right, that all these cross sections you can determine in terms of one number, if we could do everything properly, right? But that one number, right? So theoretically that is true. If you need to know that one number, you can determine all these cross sections. But in actual practice, even if somebody gives you that one number, you have to make approximations to calculate these cross sections, right? And that will introduce errors. Otherwise, ratios of all cross sections, right, which are dimensionless numbers, those will all be fixed, right? And indeed, they are fixed somehow. Theory knows that the ratios are whatever it is, and if you could have infinite power, you will be able to find all the ratios of cross sections which are dimensionless numbers. But in practice, that is not the case.
So we have to truncate somewhere the perturbation series.
Yeah, in this case, you cannot even do perturbation series because there are strong interactions, right? So you have to use other methods like lattice and so on, right? But you always have to make approximations to get these numbers.
This is even after, like, as we were saying, like, we can determine everything in terms of the coupling constant.
In principle, yes, because QCD, if you can put it on a computer, right, and solve it exactly, you would get these numbers exactly.
But we cannot, right?
We cannot, yeah, exactly.
So, in solving this equation numerically, what are the initial conditions we have to give this? Just at the initial point, what is the number density of neutron?
That you can use thermal distribution, right? Initial condition at high temperature, you just use thermal distribution, right? It doesn't really matter that much, right? You can start with ND equal to 0, right? The evolutions will take you to whatever ND are supposed to be.
Some NN and NP will give us a thermal distribution.
Exactly, exactly. So NN and NP, if you know, that is good enough.
Another input is it will start at 10 power 9.
No, you don't have to say 10 to the 9 Kelvin. You can start from 10 to the 10 or 10 to the 11 Kelvin, where things are simpler, right? And then the evolutions will tell you what happens at 10 to the 9 Kelvin. See, that is not an input you have to give, because the right hand side of the equations will know that densities are growing and the reactions are becoming important.
So this the cross section will take, like, for example, as the temperature increases, these reactions will not happen because it is more than the binding energy, the temperature.
But that again is part of these equations.
That will take care from the rate itself.
Yeah, rate, and also the point is the rate. Suppose you are trying to calculate a production of something that requires energy, right? Then that means that unless the photons have that much energy, those reactions don't take place. That information is on the right hand side, right? When you specify the sigmas, right? You cannot specify sigma to be non-zero if the rate, if it doesn't proceed, right? If it violates energy conservation, you cannot take sigma to be non-zero, right? That's also part of the data here.
Composition or the temperature at which the equilibrium cycle, those things won't depend on the initial condition.
Yeah.
But the time at which it happens, that will depend on the initial conditions, depending on what initial composition.
I mean, initially you can take to be thermal distribution, right? See, initially everything else was almost zero, so protons and neutrons are the only things present, right? And you can say that at 10 to the 11, 10 or 10, at 10 GeV, or not 10 G, I don't know 10 GeV, 10 MeV, you could use thermal distribution, right? You can take that as a starting point.
But we are also getting the table that we wrote. We also have the time value at which certain things happen.
Yes.
So that might vary depending on what initial conditions.
Usually it doesn't, because imagine that you are starting at 10 MeV, right? Or even large, maybe a little more, 15 MeV, with only protons and no neutrons, right? And you just evolve this by these equations. The equations will quickly thermalize it, right? And it will give a proton to neutron ratio which is according to thermal distribution. And then it will automatically evolve it from there, right? So because what will happen is that the converse, if you start with all protons and no neutrons, the conversion rate from proton to neutron will overcome the conversion rate from neutron to proton. So neutrons will keep getting produced till you reach the thermal distribution, right? And then this will stop, and then it will remain thermal till these other things happen, right? Till the probability of producing the other things becomes significant, right? But all those will be already there on the right hand side in these equations. Right? That's why, I mean, because of thermalization, right, lot of the initial conditions are wiped out, right? Except for the conservation laws, right? Whatever initial condition you start, if in the middle there is some range where you can argue that it was in thermal equilibrium, then basically those initial conditions are not relevant. Right? The only thing that is relevant is the total number of neutrons plus protons, because that is something that you have to give, right? The equations are not going to change that number.
Input as a constraint.
Exactly, that you have to put input as a constraint.
That means observation, the value ND over NS that we calculated is for that time at which all these
But then after then it continues to fall as 1 over lambda cube, both ND and NH.
So that we can.
That will cancel out. So the ratio will not change, right? Ratio can only change because ND and NH has gotten frozen, right? That's what you argue, that after that time. So after that, there's nothing that can change it unless, as I said, it gets polluted by production of H or D from somewhere else, right?
So, like during the star formation process or in the evolution, by this time, by the 30 million years of time, So many stars are formed, so many galaxies are.
That's true. But if you that's why I said that you have to look in regions where heavy elements are absent. Because if it was getting polluted by production inside the stars, right, then it will also have heavy elements.
Yeah, it's
Right?
densities. We can look at some particular regions.
Exactly. So heavy elements will be produced in the star, right? Of course, the D and H may also be produced. Well, H is of course always there, right? H is the fuel, but D will be produced in general. Right? But heavy elements will also be produced, right? So you look at regions where you don't have these heavy elements. Okay? That's what tells us that you are looking at regions which has not been polluted by formation inside the stars. Okay? And that's where you can trust this. You can say that the ND over NH that you get in those regions should agree with what you produced in the early universe.
Because there is not much changes happening.
Because not much change has happened, right? Unless you consider the unlikely scenario where somehow the heavy elements all went away, right? But in general, how will heavy elements go away if the others don't go away, right? I mean, once it gets mixed, it gets mixed.
I think it would help if we know temperature corresponding to this ratio, ND or N. ND or N.
No, it doesn't know. It depend on the temperature. Once ND over NH gets frozen, right? Then it will continue to remain the same ratio.
This is at the time when these reactions get freeze. Right?
Exactly.
So
Yeah.
that's the temperature.
That's the temperature. But what I'm saying, if you use the differential equation, then you don't have to talk about the temperature, right? The differential equation will tell you. You can follow the evolution of ND over NH, right? And you can also follow the evolution of T, capital T, right? And you see when ND over NH has become constant, you can read out the corresponding T from there, right? But you don't need that information for this, right? For the experiment for this measurement that you are talking about.
Yeah, you observe a patch where there is less effect of later evolution of the.
Exactly.
So one more question.
Yes.
If the initial conditions we set are such that their effects they thermalize. So components thermalize.
Yeah.
Whatever you set the initial conditions, the components thermalize, and you get today's universe.
Exactly.
So, what do we do in inflation? Why do we study inflation?
Because there's some things which don't thermalize.
And one thing, can we not say that this thermalization and reaction rates are the explanation for baryon asymmetry?
Because thermalization cannot produce baryon asymmetry, at least not based on the physics that we discussed, right?
Particle antiparticle.
Exactly.
Thermalization is just particle.
Exactly. Right? For baryon asymmetry means you have to produce more particles than antiparticles, right? So you need some reaction that can do that.
And what about inflation?
Yeah, so inflation, so basically as you said that anything that is wiped out by thermalization, you cannot detect today, right? It has gotten, whatever happened in the early universe has gotten wiped out. Inflation we will see produces some effects that is not wiped out by thermalization. Right? And those are the ones we see. The CMB fluctuations that we see, right, are the ones which couldn't have been wiped out by the early universe thermalization. Right? So any data that thermalizes, right, you cannot, that's an opaque screen that separates the early universe from us.
That's the question. Like, everything thermalizes, still we have fluctuations. So why they are that's what we study.
And then why are the fluctuations not thermalized?
Yeah.
So that's what happens in inflation. The fluctuations are such that they cannot be thermalized. Right? Because thermalization, as we discussed, right, can only influence regions over a certain scale. Right? Beyond that, thermalization cannot affect the fluctuations.
But even in that region, you will find fluctuations, right?
Yeah. So you have to evolve the inflationary data through that region. Right? That's a much more complicated process, but that has been done. Okay? So, as I said, anything that thermalizes you cannot observe. Right? So only data that cannot be removed, wiped out by thermalization is something that you can observe. Right? So when we study inflation, we will see what are such data that cannot be wiped out by thermalization. Yes.
Here we get this sigma from experiments and initial condition proton number and neutron number, or one is enough?
Only proton plus neutron number is necessary, because that is the number which cannot be changed by thermalization, right? Even if you start with all protons, no neutrons, right? Say at 20 MeV or 15 MeV, soon you will find, right, by the time you have come to about 1 MeV, that the ratio has gotten down, fixed to thermalization ratio, right? It's like if you take a box of gas, right, and put all the molecules on one side, right, and let it evolve, right? Soon the molecules will spread all over, right, and it will be a thermal gas. And after that, you can predict the behavior of the gas as if it's a thermal gas. Is this okay? Are there other questions? Okay, so this, as I said, that the current observation on ND over NH agrees with this, right? Of course, that has its own error, the observations. Right? But importantly, what this tells us is that this number you cannot change very much. Okay, if omega b h square was double of what it is, right, then the ND over NH will become half of what it is. Okay. This dependence you can, see from this general argument, right? But this will also be seen from that those differential equations. Okay, so it's so the dependence that there is a one omega b h square dependence, right? That for that you can just trust this general argument. So, for example, this tells us that all the matter that you see, right? Most of it we call dark matter. They couldn't be all baryons. Right? If omega b, right, instead of 0.04, if it was 0.3, right, it will make wrong prediction for this ratio.
If this theory is so good, why there is Hubble tension?
So Hubble tension is different. You are saying if Big Bang theory is so good, why there is Hubble tension?
If what we are studying is so good, why there is disturbance between?
Oh, it cannot determine it that accurately. H, you are saying between 0.67 and 0.73, right? That is a very small change. The ND over NH experimental ratio, right, is not determined that accurately that we can distinguish between 0.67 and 0.73. Right? The Hubble tension comes from some other sources. If that's what you mean by your question.
Yeah, I wanted to ask about Hubble tension, exact Hubble tension.
Yeah. So Hubble tension is there because, as I said, the near measurements and far measurements don't agree. Right? But this data, ND over NH, you cannot use to fix H that accurately, right? Where you can distinguish between 0.67 and 0.73.
So that error.
Because of experimental error. Experimental error is much more than this. Because you are trying to determine the ratio of deuteron to hydrogen, there are so many uncertainties, right? Even if you use all these checks that note stardust, etc., right? There is still a lot of uncertainty in the experimental measurement.
This will always constrain the combination of this omega b h square.
Yeah, so this by itself cannot distinguish between omega b and H separately. Okay, so this I just said already, but let me say that you can also determine H3 and He3 abundance. So the same method. Okay. So the order of magnitude you can get from these kinds of argument, right? If you want accurate results, you have to use the numerical, solve the differential equations numerically. Okay. There is one subtle point, okay, which is that H3 is unstable. H3 is unstable. Okay, it decays to He3 plus E minus plus navy bar. So whatever H3 we produce in the early universe, right, would have all gotten converted to He3 today, right? And we cannot really distinguish between which part is primordial and which part is produced by H3 decay. Okay. So for this, what we calculate is the total number densities of H3 and He3. He3 is stable. Yeah. So NH3 plus NHE3 over NH. This is 1.1 plus or minus 0.02 times 10 to the power minus 5. Okay. And this is observed as NHE3 by NH today. Okay, so the analysis, early universe analysis can tell you separately NH3 by NHE3, sorry, this is HE3. But the relevant quantity is the sum of the two, right? Because all the H3s will have gotten converted to HE3 anyway. No, this is all theory. This is theory. See, experimental results are typically much more, right? Because you are trying to guess by looking at the early universe what fraction is helium-3 and what fraction is hydrogen, right? Those errors are more, right? You cannot really determine those to such great detail, right? So these are results of numerical analysis.
For India or NH observations, like people can also look for
Exactly.
devoid of heavy elements.
Exactly.
And that will have a huge error.
That will have
A large error in the observation.
Yeah, typically because from the way you observe, right, you look at the spectral lines, then you see what the intensities, the relative intensities, there is so much, there may be dust on the way, right, you don't know how much, whether the signal has gotten polluted. So all those uncertainties, right, put a lot of uncertainties in these measurements, right? But nevertheless, you can, I mean, whatever measurement we could do, one can do, agrees with this within experimental accuracy.
And this also will give the same omega b square.
Yeah, this will also give the same omega by h square, because omega by h square basically appears in the numerator everywhere. So this could be one project, right? That how these abundances are measured in the in actual experiments. Or if you are interested in running computer program, you can run your own computer program to find these DNDT, write these DNDTs and calculate what abundance you expect, right? Theoretically. Okay, so there is one more thing I wanted to say about this, that this, so what we learn from this analysis, what can we learn about the universe? One, you already saw that omega b h square is constrained by this. The other constraint comes from the hydrogen to helium ratio. So remember that NHE4 over NH, this ratio, this is determined from xn of T1. T1 is the time at which T is 10 to the 9 k. right? If you look at the formula for this ratio, it basically is fixed by x and t1, right? And here, as I said, the general arguments work quite well, right, up to this 4% error in the analysis. Okay, you can of course do better by using numerical evolution, but even the general arguments can do this quite well. So now the point is that anything that changes xn of t1 will change this ratio. Okay, so you can try to compare with the observed helium to hydrogen ratio and check if it's consistent with xn of t1. Okay, and indeed the current observation of hydrogen to helium ratio does agree with xn of t1, which was 0.133. Okay, that gave this 27%, 73% ratio. Now imagine that there is that you want to change the early universe physics, right? You have your favorite model, right? You use your favorite model to evolve the universe. Okay? If that favorite model somehow changes the rate of expansion of the universe during nucleosynthesis, then that will change the T1 at which this temperature is reached. This temperature is fixed from statistical mechanics, basically. You cannot do very much with this temperature. Okay? But you can change T1 at which this temperature is reached if you can either speed up or slow down the expansion of the universe.
That is determined by the which species is dominating the epoch, right?
Yeah, that is determined by the Hubble constant at that time, right? So T1 is sensitive to Hubble constant, right? So T1 is determined from Hubble constant, from h of t at that time. Right, and h of t, if you remember the expression we used, was 8 pi g over 3 e to the 4 times 1 plus ab by 2, 2 plus 6 times 7/8 times t over t to the 4. Because this is the contribution from photon and this is the contribution from the neutrino. Imagine that there at that time in your favorite model there is one extra massless particle. So that extra massless particle will have also contributed to this. It will either be in equilibrium with photon, right, in which case this temperature will be T, or it might have decoupled earlier, right, in which case its temperature will be something that you can determine by the same kind of physics, same kind of argument. But that will add to this. Right? If it adds to this, then the expansion rate becomes faster. Right? So the expansion rate becomes faster, then the same temperature is reached at a shorter time. Right? Because the temperature is following as 1 over lambda. Right? If lambda increases faster, then the same T can be reached at a smaller at less time. And if it is reached at a less time, that means T1 is less, right? If T1 is less, then Xn is larger. Because Xn decreases with T1 because the neutrons are decaying, right? Imagine that this happened at much earlier than the T1 that you have estimated, right? That 168 seconds. Then the number of neutrons would have been more, right? Because not so many neutrons would have got decayed. And this means that there will be more helium. The helium to hydrogen ratio will be more than what we observed today, right? Or what the other model predicts, or the standard Big Bang cosmology predicts. Right? Compared to that, there will be the helium to hydrogen ratio will be more, right? If the universe was expanding faster. If it was expanding slower, then it will be the opposite, right? Because T1 will be more, so more neutrons would have decayed to proton by then, right? So when the nuclear formation starts, there are not just enough neutrons, right? So the helium fraction will be less. So this puts strong constraint on what kind of modification you can make to your microscopic model. For example, if we assume that there is one extra generation of neutrino, right? We have the three generations, E, mu and tau, right, which is contributing this 6 is coming from 2 neutrino and antineutrino, right? If you had one extra generation of neutrino, right, you are still within limits, right, of what you see in experiment, but 2 generations of 2 extra neutrinos would be inconsistent with the observed helium to hydrogen ratio. Okay, so using just this argument, right, that's the fact that you have predicted what the helium to hydrogen ratio should be and what you know what observed helium to hydrogen ratio is, that if you add one extra neutrino, you can still accommodate it, but you cannot add 2 extra neutrinos. Okay, that will be too fast, right? That will make the expansion rate too fast, and hence the number of the helium fraction will go up, right? Because there will be more neutrinos, more neutrons at the time of nucleosynthesis. Is this logic clear? Right, so this is usually used as a constraint that if somebody has changed the microscopic model for some other reason, right, you can always use big bang nucleosynthesis as a constraint to check if your microscopic model is consistent with this.
T1, same temperature is reached at early time. After that one?
Yeah, so same temperature is reached at early time. So that means xn of T1 would have been larger, right? Because xn of T1 is a fraction of neutrons, right, compared to the total number. So xn of T1 would have been larger because not so many neutrons would have decayed, right? And we know that this ratio is determined in terms of xn of T1, right? We wrote down the formula for this in terms of xn of T1, right? So if xn of T1 was larger, then that means that there will be more helium, right? Because ultimately all the neutrons get bound to helium 4, right? So more neutrons means there will be more helium 4. That if, for example, you had started with equal number of neutrons and protons, suppose xn of T1 was half, right? Then what is going to happen is that it will be only helium and no hydrogen, right? Because equal number of neutrons and protons, right? So once the neutrons get bound, right, there are no further protons left, right? Inside the helium there are 2 neutrons and 2 protons. So change in x1 gets translated to the helium to hydrogen ratio.
This is a validation of why there are only 3 types of neutrinos.
Okay, as I said, this can afford 4 types of neutrinos, but not more. Right? So just from cosmology and equating consistency of the Big Bang nucleosynthesis, you can say that there can be at most one extra neutrino and nothing more.
This by evolving the differential equation, we can this initial condition that we have to give will be at say 10 to the power 11 Kelvin or something like that. Because if you put it in say 5 into 10 to the power 9 Kelvin, it will not get that time to thermalize.
Yes, indeed. Yeah, you have to put it at sufficiently high so that in the middle there is a thermalization and then you evolve. It will automatically tell you when it goes out of equilibrium, when it comes inside equilibrium and so on, right? Those will all be contained in the differential equation. But you just start at sufficiently early so that you go through a thermalization process.
Not too early so that other...
Exactly, yeah, not too early so that the muons are relativistic, right? You can do that, but it will be a waste of time, right? So what will be wrong is that this H will increase, right? Because those will be this 6 will be, suppose you have 5 types of neutrinos, right? The 6 will become 10, right? H will increase, right? H increasing means that the value of T1 at which the temperature falls to 10 to the 9 K will be less because it's a faster expansion, right? So temperature is falling faster as a function of T. So this temperature will be reached at an earlier time. Earlier time means xn of T1 would have been larger because xn is decaying, is going down, right, with time. So if xn of T1 was larger, then that means there will be more helium to hydrogen ratio than what we have calculated. Right, because by mass we saw M He4 over mh. This was 2xn over 1 minus 2xn, right? This is the ratio that we had found by mass hydrogen to helium. So if xn was larger, right, then this ratio will be larger, right? And that will be, as I said, up to 4. It's still compatible with what we see in experiment because experiments have large error, but 5 will not be compatible, right? The 5 will increase h so much that T1 will correspondingly become smaller, right? And then we find that this becomes so large that it's incompatible with what we see today.
Helium to hydrogen ratio that we observe, it's helium, is it only free helium or also helium that is bonded in the system like stars?
Oh, so what you do is that you look in the regions of the universe which is not polluted by stars. Right? That's how one has to do this, right? But there are other ways to do this estimate, right? That inside the stars, yeah, it's true that some of the hydrogen had gotten converted to helium. Then you have to estimate that. But by doing all that, you can get a fairly reasonable estimate of the helium to hydrogen ratio in the early universe. Yeah, and that ratio is what you compare with what you predict.
What is wrong with 4 neutrons that we consider 3 neutrons only?
3 neutrinos.
Neutrinos. Yeah.
No, so you can have models with 4 neutrinos, 4 generations, right? That will increase H.
That is okay. I'm just saying, apart from this, why we consider 3 neutrons?
Because that's what you observe. Experiment, right? I mean, people have tried to find the 4th generation, for example, right? And you may find at some point, right? That's an extra generation. As long as it comes in the full multiplicative, the 4 generations of quarks and 4 generations of leptons, it's still consistent with everything. Okay? 5 will not be consistent. Right? The experiments find that there are 5 generations of quarks and leptons. Right? It will be consistent theoretically, but it will cause problem with the nucleosynthesis.
How would the measurements made, the observation that I made for this and helium to
Hydrogen, yeah. I mean, as I said, they are accurate enough. I don't remember the exact number. They're accurate enough to distinguish between 3 and 5. Right? So it's not completely, I mean, arbitrary, right? That you can distinguish between 3 and 5. So it's accurate enough for that.
So all the nucleosynthesis happens within like 100 seconds is the radiation dominated.
Yes.
So during which all the effects of antiparticles is completely washed out.
Yes, yes. Antiparticles have gone already, yeah.
That's like the initial anisotropy we gave, it's enhanced and all the antiparticles.
Exactly. Right, because the E plus E minus, right, that started becoming wiped out at 0.5 MeV. Right?
0.5 MeV is also, this is happening around 0.8.
No, 0.08. 0.08. Right? By the time the E plus E minus, most of the E plus have also gone. Right? There is still some left. Right? That's why the T nu over T at that time is not exactly its asymptotic value. Right? But soon after that, the E pluses will go. Okay, now let's turn to heavy nuclei. So the next in line is beryllium and lithium. So He3 plus He4. one is H3, so let's figure out what is H and what is H. Second one should be H. Okay. So these are electromagnetic processes. Right, because there's gamma. Okay, so these are slow processes. Nevertheless, this can happen because there is a small density of helium-3, right, during that nucleosynthesis. And helium-4 is being produced continuously. So those can collide and produce some barium and lithium.
We need to check rate, right?
We need to check rate, yeah. So sigma you need, right? So this is electromagnetic, so its rate is much smaller than the strong interaction rate that we saw, right? But nevertheless, it's there. And using all that rate, we can again put it in a differential equation for this. And oh, by the I should say another thing, that this beryllium-7 actually decays eventually by electron capture to lithium-7. Because electrons are there, right? Eventually, that's just like hydrogen, the protons and electrons combine to become hydrogen, right? The barium and electron, it will start capturing electrons, right, to form atoms once the temperature cools sufficiently. Okay. And then there is a decay process. The beryllium-7 plus E minus can go into lithium-7. Okay. So just like that case, that happens purely at the nuclear level. Here you have to first capture the electron and then it can decay into lithium. But the final result is that whatever abundance we see today of lithium-7 is actually the sum of these two. Okay, the beryllium-7 plus lithium-7, that production. Is
the final reaction is the last one is the electron neutron.
Last one is electron neutron, yes.
They are charge polymerase.
They are?
They are charge polymerase. The electron neutrons is charge.
They don't have charge. No, no, there is no charge. Oh, but this has a positive, extra positive charge. The beryllium is a one higher in the atomic number is higher, right? So it combines with electron to become lithium. So this has an extra proton compared to lithium. Yeah, so this, yes.
This is slightly elementary question, but how do you know which of these reactions are electromagnetic and which are
Oh, whenever there is a gamma invert, that is electromagnetic.
like why can't this have so strong interaction?
Because gamma means that photon can be produced in a vortex. You need a
Say without a photon.
without you cannot have energy conservation, right? You can emit a proton or a neutron, but that's I mean that process is not energetically favorable. Right? We will see helium-4 plus helium-4, right? That is not possible energetically. Right? But for this, you need a photon, right? Because you have to have something that to balance the energy, right? The total energy of this is more than that of this, right? And that gamma, once you have a gamma, that means it's electromagnetic.
Whether it's not energetically favorable.
If you put you can replace gamma by a neutron, for example, right? Okay. But a neutron, if you add up the energies, it exceeds this. Right? So the neutron is not possible. You cannot just remove the gamma, because then the energy of these two is more than that of beryllium-7, right? The extra energy has to go somewhere. Right? So some particle has to carry away that energy, some neutral particle, and that can only be the photon, right? Just from energetic consideration.
Yes, and the forward rate method and the
Backward rate in this case will be very low, because the beryllium density will be so low, right, that whatever is produced is produced. But yes, I mean in the differential equation you put everything, right? The rate at which beryllium goes away, that also you can put, but that effect will be very small.
So that third reaction, that is weak.
Third reaction, yes, this is weak.
And it will be even slower.
But that doesn't matter. We have long time to go, right? I mean, we are observing it today, right? So even if it's slower, right? Eventually, as long as it happens between the time you observe and between the time it's created, right? It will be converted to lithium. No, stars form everything.
Yeah.
Stars even for helium.
So large fraction of these elements, I assume that it would be formed inside the stars, whatever we observe.
Yeah. So again, you have to look in the regions of the universe which have not been polluted by stardust. Say anything which has gotten polluted, right? Except helium. Helium you can manage because there's large fraction of helium, right? But these trace elements, right? You have to really look in regions which have not been polluted by stardust. Right? So that is certainly, I mean, the way you have to measure them.
So whatever we will be expecting from calculating using these reactions, I mean that will be before star formation, right?
Yes, before star formation, exactly. Yeah, so all this is happening before star formation.
During this nucleosynthesis time, this is the maximum. Like after this, no more heavier elements can be produced.
Yeah, we'll see. We'll go try to go higher, right? And we'll see what happens. Yeah, so basically using this, you find that lithium 7 order 10 to the minus 10. Pardon?
The numerical.
This is numerical result, yeah. This includes beryllium. This includes beryllium 7, right? Because the beryllium 7 gets converted to lithium 7. So now let's try to go to higher elements.
In this case also we have do we have to make that check of like sigma ND X inverse is greater than 1 in these reactions.
Yeah, so this all this, I mean, if you use numerical evolution, all that is already built in, right? There you don't have to check anything. As long as you can write a computer program, right, it will do the job. Because everything is included on the right hand side, right? All the data about sigma, the rates, what the densities are, right? They are evolving them by numerical these equations.
And this is the one.
Yes.
In the theory, we saw that we need some critical density for the reactions to be take over enough number of collisions to happen.
Yes.
So in the numerical simulation, like it will always react. It will because this equations we wrote by saying that okay, these reactions will happen.
Yes.
Yeah, but first we have to check whether will this reaction happen at all.
No, you don't have to check. If it doesn't happen at all, the right hand side will be very small.
On the right hand side there are rates, right?
Yeah, the rates are there on the right hand side, right? See, it's not 0 or 1, right? It switches on, right? But that means that whether the right hand side is close to 0 or not, right? So when you say the reactions will not happen, right? That means basically the right hand side is not large enough for this to be significant.
So in the input when we give rate is also coming from the same sigma and p calculation.
Rate is a microscopic calculation or experimental measurement in the lab. You can collide two nuclei and see what their cross section is. Sigma, right? So that's the microscopic input, right? You either do it experimentally or you try to do calculate it theoretically. That's a microscopic input, right? And then here on the right hand side also there is Ni and there is T, right? But the evolution of T also you know as a function of time. So all those become part of the differential equation. So in this form you don't have to say anything about when it switches on, when it switches off. It will happen automatically. Right? Or whether there is equilibrium, whether there is no equilibrium, that will also happen automatically.
So at each and every step we have to do some rate calculation of all these reactions.
Well, you do it once and for all, right? You rate calculation or rate measurement in the lab. All the nuclei, right? You collide nuclei and you calculate the rates, calculate the sigma. From the either from experiment or if you have a theory, you use your theory.
In the numerical simulation itself.
No, numerical simulation itself, the sigmas are fixed, right?
Yeah, that's what I'm saying. Like sigmas are fixed.
As a given function of energies.
But these rates are not fixed in this reaction.
The rates depend on sigma as well as the number density. So what is varying as the number densities, temperatures, etc. right? Those are changing, right? And those are the ones which determine whether the rate is sufficiently large for this right hand side to be significant or not. Is this okay? Any other question? Okay, so the most natural thing to do, right, will be to try these. So if you want electromagnetic interaction, right, this will be some A equal to 8 plus gamma, right? This will be A equal to 5 plus gamma. See, these densities are large even after nucleosynthesis has happened, right? So these could collide, continue to collide and produce heavier elements, right? Those will be, in fact, if they could, then those will be large enough large enough numbers, because densities of these are large enough. Yes, most of the densities have gone into helium and proton. Okay. But there are no such elements, right? No stable elements of this kind. So no stable A equal to 8, A equal to 5 elements. Then you can try something else, which is say helium 4 plus helium 4 goes to lithium 7 plus P, or beryllium 7 plus N. But these ones, right, is not energetically favorable, not possible energetically. Okay. In other words, twice the mass of helium is smaller than the mass of lithium 7, and also smaller than mass of beryllium 7 and mass of helium. And this essentially happens because helium is a very strongly bound object. Right? The helium nucleus, 2 protons, 2 neutrons, have a large binding energy, right? So that reduces its mass, okay? And it's just that binds it so hard that you just cannot split up. Right? The mass of on this side is larger than the mass of the 2 helium nuclei. Right? Of course, you can say that if you have very energetic helium, it can happen, right? But then the probability of finding such energetic helium, right, because of this Boltzmann factor, e to the minus m by t, is really, really small. Right? So that's the reason why these reactions don't happen. Right? And so basically, you don't produce anything beyond atomic number 7. Okay, everything else is produced in the stars.
Because temperature is so low that MHE are
Exactly.
non-relativistic.
Exactly, because they are non-relativistic.
In stars, we have lesser temperature than this.
No, in stars you can have very high temperature, more than this.
Millions of Kelvin means like 10^6 Kelvin at the core of the star. So that is less than that of 10^9.
No, that is
At that time, it doesn't happen. When temperature goes up, then
that's MeV, right?
So I'm talking about in the star, most of these reactions will happen at the core of the star, and at the core of the star we say the temperature is of the millionth order.
No, it's a lot of 10 to the 10.
Yeah, at 10 to the power, then these reactions happen. At 10 to the power 6, only first reaction helium, other than the helium can happen. For higher reactions, we have to
Star temperature I have to check.
What?
Temperature of star I have to check. And what temperature?
Yeah, I think that for heavy production of heavy elements, you need higher temperature.
Maybe you guys are confusing MeV and Kelvin.
No, believe. I see. Yeah, I think yeah, you need more temperature than this to produce these elements, right? Because otherwise, with non-relativistic helium, we are not going to get these.
And the density is also high, so number of
Exactly, the number densities are high, right? So even if the probability of producing is small, right, it can get compensated by the number densities. And the time scale over which you are having these collisions is huge, right? Not in seconds, right? You can wait for a long time inside the star.
Okay, so even if there is small fraction of who have enough energy to produce this, I mean, to undergo such reaction.
Exactly, yeah.
Because we have enough time.
Because you have enough time. Okay, so this is as much as I'll say about nucleosynthesis. So let me just say what we'll do next, and then next time we'll start with the next topic. So basically we move forward from here. So there are various events in time that we can discuss. So some of these are that photons go out of equilibrium. Then the helium captures electrons. Okay, this becomes He plus, and then to neutral by capturing one more. At some point, universe goes from radiation to matter dominated. Okay, this one we had already discussed earlier. Okay, remember how when the universe becomes from radiation to matter dominated, we just equate the energy densities of matter and radiation. Okay, but with all that we have learned, there is going to be one change in what the condition that we had written down earlier. Okay, so equate the radiation density to matter density. So half AB times so rho C again is 3h naught square or 8 pi g. Okay. So the only difference earlier you had said we equate the radiation energy density of the photon to the energy density of the matter. This goes as 1 over lambda cube, this goes as 1 over lambda to the 4. Right? So at some lambda this will become equal. Okay. Now we see that we also have to add the contribution from the neutrinos. Right? Because they are also contributing to radiation energy density. Right? So it's the sum that we have to equate to this. Right? This just makes an order 1 change in the value of lambda at which this happens. Okay, and the final thing that which will take the most of this part of the lectures, this part of the course, is the recombination or large scattering. P minus binds to P. Okay, and this at this stage the universe becomes transparent. Okay, so next time we'll discuss this quickly. These two will not do very much because, I mean, even though these are events that happen, right, they don't have any direct bearing on what we see today, right, because the universe was still opaque at this time, right, so you cannot directly observe them. This is the one which we'll discuss in detail of exactly when it happened, right, because this is important because we are saying that it happened at some value of z, right, and what we are seeing is the image of the universe at that value of z. How do you know what value of z it happened? Right? And that requires a lot of theoretical analysis, and this is what we'll study in this part. Okay, as we'll see that you can use equilibrium physics, but equilibrium physics is not totally accurate, right? Then you have to use actually non-equilibrium physics to figure out what happened at this time. Okay, so I think I'll stop here today. Yeah, basically what happens if there is some kind of phase structure, suppose there are some heavy objects which decay, right? That can produce gravitational